Good evening, guys. Today we are going to see the concept called logic gates in digital electronics. Uh, there are like different types of gates which are present under digital electronics. Those are framed or constructed using diodes, transistors, and resistors. Let's see how different types of logic gates are visible and constructed under this particular concept. Let us see. There are These are different types of logic gates which are available. Those are AND gate, OR gate, NOT gate. Apart from these basic gates, we are having other universal gates called as NAND gate and NOR gate. Why? Because using these two gates, we can construct any type of other gates. Like AND gate, I can construct, OR gate, I can construct, NOT gate, I can construct using NAND gate or NOR gate. And other than this gates, we are also having XOR gate and XNOR gate. So these are the gates which are present for our digital electronic circuit constructions. Let us see individually, independently how these gates are visible. Now, for example, if I am having an AND gate. Now, for AND gate, how does it look? So this is the symbol for AND gate. Now you can see you have two input terminals with output terminal as Y, and the output of AND gate is represented as A dot B. Now Boolean expression for AND gate is Y is equal to A dot B is the Boolean expression for this particular thing. Let us see how the functionality of AND gate visible for us. Now AND gate of the functionality is given by the truth table. This is the truth table. Now this truth table represents two input variables and output variable. Now two input variables can have four different combinations, that is 0 0, 0 1, 1 0 and 1 1 combination. Now output of AND gate is high only when both inputs are high. If both inputs are not high, then output remains low. So this is the definition for AND gate. Now the construction can also be seen using diodes and transistors. Let us see diodes and transistors. Now you can observe clearly that here we are using two diodes, that is X diode and Y diode as input terminals through which I am going to supply inputs and which are going to produce output at Z, with a resistor R in parallel to the connections of my diode. So V is the voltage which is applied. So the output is going to produce an AND combination of X and Y with the input terminals connected to a diode. So this is what the connections which produces the AND operation using diode operation. Okay, let's get on to the next gate, that is OR gate. So this is the OR gate here. Now this is OR gate contains two input terminals A and B with output terminal as Y. Now here the operation between A and B is given as a plus symbol, that is Y is equal to A plus B, whereas before gate it was A dot B. Now here it is A plus B. The Boolean expression for OR operation is Y is equal to A plus B here. Now let us consider the functionality table for OR gate. Now OR gate functionality is whenever any input is high, the output remains high. If both the inputs are any number of inputs, if it is having three inputs also, if all the inputs are low, then output is going to be low. If any one input is high, the output remains high. As two variables, I am taking four combinations. Now if you observe, both inputs are 0, the output is 0. For remaining all combinations, my output remains high here. So this is what the construction of an OR gate. Let us see the construction using diodes. Now this is the diode constructions. Now if you observe, VA and VB are the two voltage supplies which we are providing to diode D1 and diode D2 with a load resistance connected at the output terminal, and Vout has been taken as output voltage. Now this particular combination is going to produce OR operation for diode D1 and diode D2. Whenever one input voltage is high, the output is going to be high. If both the inputs are low, then my output is also going to be low. So this is what the operation which is constructed using diodes. Let's get on to the next gate, that is NOT gate. Now this is a very simple gate. You will be having only one input, one output, out with input A and output as Y. Now Y is will be given as a Boolean expression, Y is equal to A bar. So the Boolean expression is produced as y is equal to a bar. Now let us see the functionality table. How does it look? Now if you observe, it is having two inputs, that is, sorry, one input a and output as y. If input is 0, output is 1, input is 1, output is 0. Now the same construction using a transistor. Now if you see, observe clearly, a transistor which contains emitter, base and collector. These are three terminals. Now this emitter is grounded, whereas base is connected to R2 resistor and collector is connected to R1 resistor. R1 resistor is connected to VCC voltage and output is taken across the collector region. Now if I am producing, I am putting an input logic at A terminal along with my VCC, then this particular gate is going to act as open circuit or closed circuit based upon the logic provided. If I am giving logic 1 as my input, then this particular transistor is going to act as closed circuit, so that the total current will be grounded here and output is going to produce a logic 0. When I am producing putting input as logic 0, then this particular transistor acts as open circuit, total current will be taken as output, then a logic 1 will be my output. So this is the operation of a NOT gate. Now let us get on to the next gate. So this is the NAND gate. NAND gate which consists of two input terminals A and B and with output as Y. Now a normal AND gate connected with an inverter gives a symbol called as NAND gate. Now the same, this is exactly opposite operation of AND gate. Now see, for 001, for 011, for 10 is 1, 11 is 0. So this is exactly opposite operation of AND gate. Coming to NOR gate, it is exactly opposite operation of OR gate. I am connecting a NOT gate in front of a OR gate, which is giving me a NOR gate. So this is a symbol for logic gate for NOR gate. Now the expression is given as y is equal to a plus b whole bar. Similarly, for a NOT gate also, the expression is y is equal to a dot b whole bar. So this is what the two different symbols for a NAND gate and NOR gate. Let us see XOR gate. These are special purpose gates where you can see a arc separated with a gate with inputs A and B and output as A exclusive B. So exclusive symbol you can observe clearly. So this is the exclusive symbol which is given for XOR gate. Now let us see the functionality table for our XOR gate. Now for XOR gate you can observe clearly the output is going to be 1 when differential inputs are applied. When in the same inputs are applied, output is going to be 0. So XOR gate works only when differential inputs are given, and for remaining cases the output is going to be 0. For XNOR gate means I am connecting a NOT gate in front of an XOR gate, I am going to get a XNOR symbol. Means for a differential input it is going to give you a 0 output, and for same inputs output is going to be 1. So this is the symbol for it, and that is A exclusive B whole bar, and XNOR option operation can also be represented as A XNOR B. So this is also one more symbol for A exclusive B operations. Now let us see the functionality table. It is similar to that of our XNOR. Now see here, for 0 same outputs, output is 1, for differential inputs output is 0. So this is what the gates. Now why we are calling NAND and NOR gate as universal gates? Why? Because you can see I am using a NOT gate using a NAND gate. So I am connecting one input here. If you clearly observe here inputs, I am taking an input which is connected to an NAND gate. So A dot A whole bar is equal to A bar. Means I am giving A only, but output I am getting as A bar. Now if I am giving 0 0 as input, NAND gate 0 0 will produce as 1. If I am giving 0, it is giving as 1. If I am giving it as 1, it is going to produce as 0. So it is acting as NOT gate. Similarly, if I get on to the AND gate operation, if I am getting into the AND gate operation, also this is the AND gate operation. If you see here, A and B are the two inputs which are given to NAND gate, that is A dot B whole bar. A dot B whole bar I'm having. For this one, A dot B whole bar, I'm connecting a NOT gate. So this was a symbol which was I used as NOT gate operation, where I'm going to get A dot B. So I'm getting a AND gate operation using NAND gates. So this is how we achieve AND operation using NAND gates. Let us get on to OR gate. So this is your OR gate. Now when you observe this clearly, an OR gate, so I'm taking two inputs, A bar, B bar, using a NOT operation. I'm doing, I'm connecting it to a NOT gate. So that is NAND gate. That is A bar dot B bar whole bar. Now when I'm applying a De Morgan's law here, if I'm taking bar inside, this becomes A plus B. So this is giving me a OR operation constructed using only NAND gates. So NAND is a gate where I can perform NOT operation, AND operation and OR operation. So that's the reason we call these gates as universal gates. Let us get on to NOR gate also. How like NOR gate is. Now the same thing that how we constructed, you can see here in NOR gates also. NOR gates you see A and B constructed using. Now here NOR gate can be used to get to the operation of NAND also. That is, we are connecting an inverter at the output terminal to get NAND operation. So this is how. Now XOR gate using NAND also. So this is what the operation, you can see A and B, A bar, A dot B whole bar, that is called A bar plus B bar, which I am constructing, which gives us an operation of A exclusive B. So these are the operations how we construct using NAND gates. Similar in the similar way we are using for NOR gates also. NOR gate with only one input here, and output I am getting it as A bar. So 0, 1 I am going to get. If I am giving 1 as input, output as 0. So this is how the construction goes. Similarly with all the gate levels for OR operation, for AND operation, for NAND operation, XOR operation and XNOR operation. So these are how we are going to implement NAND and NOR gates to implement all other gates. Okay, thank you. We'll continue in the next topic.